All right, class, so today we're going to be starting chapter 1, which is an overview of discrete mathematics. Some of these things are going to seem a little familiar because you may have covered them in my finite math course or in college algebra, but we're going to dive into them a little bit deeper so we can build ourselves up to mathematical proofs and creating mathematical proofs about halfway through the semester. So the first thing I want to introduce you guys to is the concept of what a discrete graph is, right? We're taking a discrete math course, and I haven't even told you about what that is. So the first thing I want to do is a function refresher. And if you remember all the way back to last spring in college algebra, we talked about vending machines. But the first thing I want to do is discuss what a relation is. So friendly reminder that a relationship is a correspondence between a set X and the domain, and we call that the set X, which is the domain, and our set Y, which is called the range. Now in this course, we're also going to call the range the target. So for example, a relation is any set of ordered pairs. We can define relations just as a set of ordered pairs. And we're right, we could graph these on a coordinate plane. We could describe it as a table of values, a graph, which is what we're going to focus on in this section, or as an equation or rule. And we need to know what a relation is and how to define it in order to determine if a relation is a function. Friendly reminder about the domain and range. So if I have X and Y, which are two non-empty sets, right? Remember, a set is a collection of objects, either finite or infinite. A function from X to Y is a relation that associates each value of X with exactly one element of Y. Okay, so a function is where each X has exactly one Y value. And I discussed this in college algebra using a vending machine. So we've got our vending machine. It has buttons, CD, that's not a button. How about C6? And D7 and E8, right? And we've got our Snickers and chips and Coke, okay? So the buttons are my domain. They're my independent variable. And what my range, or now what we're going to call our target is what comes out of the vending machine. It's what depends on the independent button that we push. So this vending machine is going to work, right? If I push C6, I get Snickers. If I put G7, I get chips. If I push E8, I get a Coke. Because each X value, in this case, is exactly one Y value, this is a function. Okay? There's one other way that we could write a function. Well, there's lots of ways we could write a function, but one other type of function I want us to look at is what if I have, instead of D7 going to chips, D7 goes to Snickers. Will this vending machine still continue to function? It will, right? I push C6 and I get a Snickers. I push D7 and I get chips, okay? When will our vending machine not function? Well, our vending machine will not function if I had C6 going to Snickers and going to potato chips. This is not a function. Why is that? Because if I was to push C6, what do I get back out? Do I get back out Snickers? Do I get back out potato chips? I don't know. So this breaks our vending machine, and therefore it's not a function. We're going to be focusing on things that are functions in this section. So let's go ahead with these three examples and state the domain and range, which we're now going to call the target, and determine whether or not it's a function. So for F, my domain, which I'm going to represent with a D, is the set of numbers 1, 4, and -1. I'm going to go ahead and write those in numerical order. My target, which we used to represent with an R, now we're going to represent with a T, is the numbers -2, 2, and 5. And for this function F, this relation F, which is also a function, oops, I gave it away. Okay, well, I have 1 goes to 2, 4 goes to 5, and -1 goes to -2. So if f was a vending machine, it would still work, so this is a function. Let's switch colors for clarity. So our next relation we have defined is G. Our domain is -3, -2, -1, and 0. Our range is 5. I already wrote 5 down once. Remember, each element has to be unique. And I said range, but I meant target. But remember, they do mean the same thing. So I've got 4, 1, and 5 are my target or range. I have that -3 maps to 5. -2 also goes to 5. -1 goes to 4. And 0 goes to 1. If this was a vending machine, would it function? Yes, right? It's okay that I have -3 and -2 both going to 5. So this is a function. I bet you can guess whether this last example is going to be a function or not, but just in case, let's go ahead and work through this one. My domain is -1, -2. Remember, I write each element once. We're going to talk about sets further on in this chapter. If you still have your college algebra text, which I hope you do, I believe we talked about it in the beginning of chapter 1. If you want to go back and take a quick look before we take a deeper dive later on. Our target is 0, 2, and 1. So I have that -1 goes to 0, -2 goes to 2, and -2 goes to 1. Notice that my domain's on the left and my target's on the right, just as a thought. So this is an example of something that would not function. If I push -2, what do I get? Do I get a 2 or a 1? I don't know. So this is not a function. Remember that functions can also be represented by graphs. And in order to check if a function is a graph, we can use the vertical line test. So what a vertical line test does is it says that for each vertical line going through a function, I want to make sure my vertical line intersects the graph only once. So here for this, remember this was a linear equation because its graph is a line. And here we have a parabola, also known as a quadratic equation. It's also a function because each line I go through it intersects the graph only once. Some things that are not functions would be this rotated parabola over here. As you can see, I have 2 y values for 1 x value. Same thing with a circle. This is not a function. When we say a function is defined with an equation using x and y for our independent variables, we often say that y is a function of x in order to emphasize that y depends on x. So we would write this as f of x, so a function depending on x. It doesn't have to be f of x. It can be g of x, it can be h of x, but as long as we know that this notation tells us it's a function that depends on x. Here are 2 really common linear functions we have seen before in college algebra. So for example, a linear function where y equals mx plus b, m is our slope, this should ring a bell, b is our y-intercept. We aren't really going to be working with these types of functions a lot, but I wanted to let you know that you have seen and worked with functions before. Next is a quadratic function, right? This is a parabola, sometimes called the squaring function. Its domain is all real numbers, and in this example, its range or its target goes from 0 to infinity. Now, what's interesting about these 2 functions, the quadratic function, whose domain is all real numbers and ranges from 0 to infinity, and the linear function, whose domain is all real numbers and so is its range or target, is that we express these as an integral, right? Remember, this is interval notation. This goes all the way from negative infinity to all the way to positive infinity. Same thing's true with a quadratic function. We express its domain as an interval. In discrete math, we work with domains that are not intervals. We work with domains that are distinct states or configurations, okay? That sometimes means that we have a finite amount of objects in them, or they only can take on specific values. What do I mean by that? Let's work through an example.